the many open windows that I have. Okay, so hi everyone, good afternoon. I hope for a start that you still have a few uh, s- have some energy actually left. I know that you will be very tired. I understand that. So I'm going to be brief. So in this presentation, I'm going to talk about a project that started a few months back. So this project is about investigating SEP events with extreme electron-to-proton ratios. And this was part of the heliophysics guest investigator solicitation in 2023, and we have kicked off this project 2 months ago. So the team comprises of me, David Lario, Ian Richardson, Angelos Vourlidas, Bob, and Athanasios. We have so this is the team that will be involved in this project, but everyone is welcome to get aboard. The period is for 3 years, and I'm going to show you a few details of how we constructed this project and what's the final goal. So there has been a long-standing debate about the mechanism that can accelerate protons, electrons, and heavy ions to energies ranging from a few 10 of keVs to several GeVs a few minutes after the start of an eruption. So in principle, there are several different mechanisms that they can be responsible. There are a few here. So acceleration associated with solar flares, so flare-related mechanisms, or accelerated at the CME-driven shock. I will call them shock-related mechanisms. The contribution of these mechanisms has been difficult to determine, and there are a few open questions. All these different mechanisms are usually expected to act differently on electrons and ions due to their different charge to mass ratios primarily, but also some details on each of the acceleration mechanisms. So I don't usually like this dichotomous separation of SEPs because many studies have shown that this picture it's a little bit more complex, but it's convenient to construct here my story. So in one case we have impulsive SEP events. You can see here a few characteristics of the impulsive events. Usually this event comes in close association with type 3 radio bursts. That's one important element that it's important, I mean, for the project. Composition enriched with helium-3 in many cases, and high electron-to-proton ratios. And usually we have a small angular extent. On the other hand, we have large gradual SEP events, which are associated with fast shocks, strong type 3s and type 2 radio emission. It has been observed lower electron-to-proton ratios, and they usually have a larger extent. Of course, as I said before, not many of these events conform to this simple class, and sometimes it's critical to understand if there is a continuum or not, and what's the extremes and what properties they have. So, as I said before, the relative role of the flare and shock accelerating mechanisms in accelerating electrons and ions to high energies, it's a little bit ambiguous, and this project will primarily focus on the high energies. So let's say electrons above 700 keV and protons above 20 MeV, but our threshold is a little bit more, let's say 50 MeV. The capability or efficiency of the shocks to accelerate energetic electrons to energies above few hundred keV or jet flares to accelerate high energy protons is not yet clear. Well, I have a mistake here to accelerate. Yeah, I was talking about MEV protons and high energy protons here. Nevertheless, electrons can be accelerated in large amounts during impulsive or gradual events, and this is what we see from let's say, in situ observations and remote sensing stuff, type 3s, type 2s, etc. So on the other hand, high energy protons are not always present in small impulsive events, and this is what we usually see for a few events that only have high energy electrons and lacking some high energy protons. So a question arises to whether the electrons and protons has the same origins, and if not, what happens, and see details of the mechanism involved. So for gradual events, one scenario is that the flare-related mechanism is the main source for the high energy electrons streaming away from the sun and observed later in situ. Another scenario is that strong shocks may also be capable of efficiently accelerating electrons to high energies. You may have seen some latest studies. Whereas electrons of tens or hundreds of keV are primarily accelerated by magnetic reconnection processes, and somehow they find their way out during jets and flares. Now, for impulsive events, there is no clear consensus for the high energy protons. And this is where we come up to what we want to address actually in this project. So we want to examine SEP events with extreme electron-to-protons ratios. This metric has been used in previous studies, and this is an example, a figure that it's based on results from Kane et al. And some results from Richardson that shows, the electron-to-proton ratio for many events. The bottom is I think the proton flux, and you can see how these events are distributed. And here we have marked the different events with some colors according to some distinct characteristics based on Richardson classification. So, for example, the red, it's electron-rich events. Some other events, they have weak shocks or no shocks, yes shocks, etc., etc. So we will investigate SEP events on the tails of the distribution that exhibit extremely high or correspondingly low electron-to-proton values at high energies, include events where detectable high energy protons or electrons are absent. So in some cases where we only have high energy protons, or some other that they have only high energy electrons. So in principle, our main focus will be here at the very end of this distribution. Okay, these events here. So we think that little attention has been given to these cases and their specific characteristics. However, they may hold a key to a better understanding of differentiating the relative role of the different mechanisms into the acceleration of SEPs to the high energies. So first, we aim to identify groups of SEP events with the extreme values of electron-to-proton ratios, and contrast, the circumstances of their accelerations at the sun. This will be no. I will explain this later. So our main objective is to perform a thorough study of events, compiling a comprehensive catalog. We want to address three main questions. What are the main properties of these extreme events? Solar associations, ion composition, connectivity, and interplanetary context. What do these properties and associated activity may tell us about the underlying acceleration mechanism? And in the end, if we can unambiguously discriminate signatures of single particle acceleration, either by magnetic reconnection or by some shock-related acceleration. So the data, the methodology is the following. We will use data from multiple heliophysics missions, both in situ and remote sensing. Our primary focus will be stereo, solar orbiter, and SOHO, because we have plenty of observations, especially now that we are on the almost fourth year of observations from Solar Orbiter. We have plenty of events there. And for the past missions, we understand very good their data products. So we thought that stereo and SOHO, it's a good start, and then we extend the analysis for Solar Orbiter. So this is briefly the list of data that we will use from stereo impact ahead. We will use both electrons and protons, Solar Orbiter EPD head, electrons and protons at these ranges, SOHO, ERNE, and EFIN, again, protons and electrons. We will supplement this analysis with remote sensing stuff from various instruments, stereo, SDO. We want to, for example, make the solar associations. We want to make magnetic connectivities, as I said before. We want also radio data that will give us associations with the different radio bursts. Also soft X-rays. And this actually, all this is going to be a task to compile, let's say, a final catalog and start exploring things. So the different tasks, you can see here the different tasks throughout these 3 years. We have a lot of things to do in order to prepare, firstly, the data, because we have 3 different spacecraft. We have to make sure that the comparisons between the data are good. I mean, we have the right, let's say, calibrations. Then we have to do our SEP data survey to recognize the events. This is an example from Solar Orbiter between January to July of 2022, and we have just for the visualization of the things a few candidates here. Then we have to characterize the SEPs, characterize the properties of solar activity. Maybe we can select some case studies and see individual events if we find something interesting. We already have a few cases in mind, and then we will proceed to some statistical analysis towards the end of the project. And this is where I will thank you for your attention. And as I said before, the 2 projects, I mean, Spearhead and this one, I think they are very complementary. And I hope, the people that involved in Spearhead and also working with me on my project, we will closely collaborate. Already we have done that for a few studies. So yeah, let's look forward to the results that we will have. And that's it.
Thank you very much. Let's thank our speaker. Any questions, comments? Oh, Rami, Bernd, you're monopolizing.
Thanks, Thanasis. Interesting. So I just wanted to say that we have a paper submitted to AAD about these quite extreme electron-to-proton ratios, as you might know. So from Serpentine catalog, we already saw that there were some interesting things like what you seem to indicate actually in your plot as well. So if you are looking at the extreme cases where there are a lot of electrons, these are usually related to low proton fluxes, not so much on so you wouldn't get these extreme electron-rich events for very strong proton events at all. Of course, this is quite natural because there might be a limit of how many electrons you can actually accelerate, and then the only way to get higher ratios would be to not accelerate protons. But this Serpentine stuff will be also probably very relevant to this as sort of background information.
Yeah, this is great news. Yes, indeed. And this is so these cases are events that they are widespread. So because I remember that for the Serpentine you primarily focused on multi-spacecraft events, so I would expect that some of these cases it's not the standard, let's say. Uh, uh, impulsive events that have small angular extent, etc., etc. So they are in the case of the large gradual events that so exhibit this characteristic, right?
Yes, so this is based on the catalog events. So all of these are multi-spacecraft events, but they are not necessarily widespread ones. So it just requires 2 spacecraft to observe the same event.
That's it. That's even better. And yeah. Thank you for the information.
Yeah, this is Ben speaking. So thank you very much for this very interesting and nice talk. Just would like to add, we have a student, a PhD student, which is working on the electron data. So the fluxes of these things can be very different to what have been in level 2 data and so on. So maybe we should get together in order to work with him. So that you get really electron fluxes, which we now believe, which we could really publish and not use anymore the rates. So that
this is a great thing. And so you're talking about which mission or any mission? So because
we are talking about the EFIN experiment. So this is
the EFIN, yeah, and that's a very good comment, because especially for the EFIN instrument, it was let's say a hard task for me to discover where are the available data and what's the status in there. So that's very good to know, and yeah, we will definitely keep in contact to make sure that we will have the right data, as you said. Yes, thank you.
Yeah.
Okay, any other comments or questions? Nobody, everybody's really tired. Good, okay. So thank you, Athanasios, once again.
You are very welcome.